We have two particles connected by an inextensible string. We add their weights, 2 mg and mg, a reaction to the rough table at A, and a limiting friction F equal to mu r. There will also be equal tensions, which we denote by T, as the pulley is smooth. Particle A is held at rest on the fixed rough horizontal table at a distance d from the small smooth light pulley fixed on the edge of the table. We let little a represent the acceleration of both of the particles. We're told mu is less than a half. We're asked to write down the equation of motion for A. Resolving vertically, r equals 2 mg. Applying F equals ma for A, T minus mu r is the net force towards the pulley, and this is accelerating the mass of 2m with an acceleration small a. Applying F equals ma for B, the net force acting on B is mg minus t, and this is accelerating the mass of m with acceleration small a. Adding the two equations eliminates the tension and leaves us with an equation which we can rearrange to give an expression for A, 1 minus 2 mu g divided by 3, which is what we're asked to show. We're asked to find, in terms of gh and mu, the speed of A, the instant at which B hits the floor. We can use v squared equals u squared plus 2as. The final velocity v is the velocity we need to calculate. The initial velocity will be 0. We know the acceleration is 1 minus 2 mu g over 3. And we know the displacement s is h. So we can rearrange this to get an expression for v in terms of mu, g and h. After b hits the floor, A continues to slide along the table. Given that mu equals a third and that A comes to rest at P, find D in terms of H. So now there's no longer a tension in the string pulling the particle that was at A. We still have the weight, 2 mg, and the reaction, also 2 mg, and the friction, mu r, which will now be a third times 2 mg. There's a displacement of h because the particle at B has moved a distance h. The initial velocity will be the velocity of B when it hits the ground. We know that u squared equals 1 minus 2 mu gh over 3. Substituting mu equals a third into this expression here, we can see that u squared will be 2gh over 9. Let's assume the new acceleration will be A2. Mu is a third, r is 2 mg. The friction, minus mu r, will be 2ma2, and so we can calculate A2 equal to minus g over 3. Then we apply v squared equals u squared plus 2as. The initial velocity is this u, where u squared equals 2gh over 9. V squared will be 0. We know that A equals minus g over 3, and we have a displacement s. Rearranging it, we can see that s equals h over 3. So to find D, in terms of h, D will be s plus h, so it will be 4h over 3. We're asked to describe what would happen if mu equals a half. If mu equals a half, we look at the original expression for the acceleration at the beginning of motion, and we'd see this acceleration is 0. So if mu equals a half, A would be 0 for the initial setup, and so the system would be in limiting equilibrium.